there's going to be some other people popping in here too, so let me let them in. All right, so it says a block of mass 4 kilograms is attached to a spring constant 100 newtons per meter, and the block is pulled out 2 meters. So just a quick sketch of what's being depicted is, something like this. Can you guys see my screen okay? Alrighty. So something like that. This is for 100 newtons per meter, and it's being pulled outwards a distance of 2 meters. All right. So question number A says calculate the period. So that's pretty straightforward. The period's going to be based on the formula 2 pi times square root of m over k. So you just plug all the numbers in there, and it's really not a big deal. So I'm sure you don't think this is the hard part, and you said just as much at the beginning that you had no trouble with that. Now, the next question is, what is the speed of the system when it passes through equilibrium? You got a number of ways to attack that. You can just memorize what Vmax is for a spring mass system. We talked a little bit about that in class, but you could also just do 1/2 k a squared for the amount of energy that was put in the system and set that equal to 1/2 mv squared when it passes through the center. It's something from first semester. The conservation of energy would be effective here too. And when you do that, you're still solving for V, which gives you square root of k over m times the amplitude. And that'll give you what the Vmax is. But you said you had no trouble with A and B, right? There's a number of ways to think about B. This is the way that I would have suggested you consider it when we talked about it first semester. Because if you pull the spring out, and the spring is all stretched, so right now all that energy is in the elastic potential energy of the spring, and when you let it go, the spring will be pulled, the spring will pull the mass in, and when it makes it back to equilibrium, there'll be no energy in the spring because it's not pulled out at all, but all that energy now will be in the form of kinetic in the box. So, we can look at it from conservation of energy, but also we have this motion equation that we know about now for oscillators, that our oscillator has this kind of back and forth motion, and the velocity is always trending between, a maximum in one direction or a maximum in the other direction. Well, this part is the part that tells you when it's at its maximum, and this part has to be the maximum. So either of those will work, or either ways of thinking about it work. They mean the same thing. Well, the negative sign indicates direction in all of these. So the negative sign appears here to indicate that the velocity of the object tends to oppose its displacement. So if you pull it outwards, it's going to go back inwards. If you push it inwards, it's going to come back outwards. But if they're just asking for what the maximum speed is, then speed doesn't have direction. You just need to figure out how fast it's going. Was it 10? No, I don't know. What is it? No, that should work out too. Because question number C is going to ask how much energy is in the system. And that's just going to be 1/2 k a squared. That's how much energy is put in the system right in the beginning. and that's going to be 200 joules, I think. So, well, yeah, it's. I mean, I don't want to say equivalent because one's potential energy and one's kinetic energy, but it's the amount of energy that is stored in anything that's elastic when you've gone to deform it, when you've stretched it out, or when you've pushed it in. And that, yes, it represents how much energy is stored in that elastic system. Would it be the same as what? A represents the only difference, and I want to be careful about this, is X can be any displacement of the spring. So as the object is oscillating back and forth, it might be part way, halfway to its maximum, and you might be asked, well, how much energy does it have in the spring now? But A signifies that it's at its maximum. X can be someplace else. So I say it like that because in an oscillating system, the total energy is going to remain the same. So when you're stating that you're looking at the position when it's at the amplitude, you're stating the point at which all the energy is in elastic and none is in kinetic. So that's why I want to be careful here. We talk about the energy of the system. The energy of the system is based on the amplitude of the system, and that's the maximum displacement, not just any point in the system. Well, the difference is what they both reference a system where energy is stored between two objects that are interacting through a force. So you want the difference between gravitational potential and elastic potential. The gravitational potential, the interaction is the gravitational force. So the two things are storing energy, in a force of gravity between the two objects. We say MGH because on the Earth, when you're close to it, the force on objects is, the acceleration experienced by objects is always the same for all objects. So we can just talk about how far away we are from the surface of the planet. But gravitational potential energy can be any two objects and their gravitational interaction because they're connected by gravity. All objects are. Elastic potential, they're connected by a spring or elastic force. So there has to be, the object, you can only have potential energy if there's a force that connects the two objects together. And for the elastic potential energy, it would have to be something elastic that was in contact with your object and then something that fastened the spring together. So like if you'll notice I always have a wall here, something I attach the spring to indicate that the spring is fixed in place on one side and it's interacting with the object on the other. And in order for there to be energy stored in the spring, there has to be some displacement of the spring. It has to be stretched or deformed away from its original shape. Basically, you have to do work to pull out the spring or to push in the spring, just like you would have to do work to lift up an object to give it gravitational potential energy. So if an object is changing height, we would talk about gravitational potential energy. If an object's interacting with something that's elastic, we talk about elastic potential energy. You're just picking one and explaining your reasoning, but the red graph is the position graph, and the blue graph is. Go ahead. That's one thing you can tell right away is because the amplitude is 2, even though it's not labeled. The other thing, which is not as obvious, is the fact that at time equals 0, the object is starting away from the origin because it was pulled back and released, and when it was released, that represents time equals 0. And the blue graph, if you look at it, at time equals 0, the velocity is 0. but it's also, the velocity is immediately negative, indicating the object was pulled back towards equilibrium.